Welcome to Lesson 9 of Math 135. Today we're going to be talking about inverse functions. And I don't want to get into a lot of stuff about roots within the language, but I think inverse and reverse ought to be thought of kind of together in this particular lesson. Okay, to start out with, we want to look at this particular function. We're going to call him g, and he's just this nice little linear function. And I've got his graph here in purple, this 3x minus 6. Now, I know that you guys know all about this, but I'd like to make a table of values. If x is negative 2 and I put him into g, I get out a negative 12. And it's a little bit hard to see because it would be off of this screen, but the negative 12 would be down here below where our graph goes. When x is negative 1, if we plug it in here, we end up with a negative 9. And you can see the negative 1, negative 9 sitting there as an ordered pair. If I plug in 0 for x, I get a negative 6, and we see that point on the graph. 1, negative 3 is on there, and 2, 0 is on there. So we have those particular order pairs on there, no big surprise. And then what I want to do is talk about the inverse of g. And in the case of doing an inverse, what we need to do is we need to go in reverse. So what we do is interchange our x and y. So this point, negative 2, negative 12 off of g, he's going to become the point negative 12, negative 2 on the inverse of g. Now, of course, if I try to plot negative 12, negative 2, he's off the graph, so I'll just let him go. The point negative 1, negative 9, when I reverse him, becomes negative 9, negative 1. And when I plot that, it's going to be about here. And the 0, negative 6 is going to turn around in reverse order to negative 6, 0, which is about there. 1, negative 3 in reverse is negative 3, positive 1. And he goes about here. And then 2, 0 becomes 0, 2. Okay? And he goes about here. Now you realize that I could actually find all of these points and then reverse the order on all of those. And so eventually I would get all of these points filled in. And if I could draw a straight line, there would be the graph of g inverse. Now as you look at that, you might kind of notice something interesting about the graph. I have an extra line in there, and you might have wondered what that was doing there. This blue line running up through the third quadrant and the first quadrant is the line y equals x. And one of the really interesting features about the graph of a function and his inverse is that they are reflections of each other over that y equals x line. That makes kind of a nice little way to test yourself as to whether you've got a good graph for the inverse. Okay? So I've got a lovely graph of the inverse of a function from the graph of the original function. Now, you know me by now maybe if you've watched these other episodes, and I've got a little bit of a strange bent. When I was trying to think about the idea of an inverse function, and you know, last lesson when we were talking about composition, we talked about having an assembly line and putting together a speaker, stereo speaker. Well, I didn't want to try to do that all in reverse, so I decided to employ a monkey. And so I asked my monkey to make up this nice little routine. So he does 3 little hops and a big hop. Gets in his house, and then he does a cute little curly cue to come out. And I said, now that is your function. Your function is 3 hops, big hop, curly cue out. Now I want him to go in reverse. Idea is that inverse functions are going to undo each other. They're going to go in the opposite operations. So I asked that monkey to please take a short rest and then come back, and now please reverse yourself. There he did his curlicue backwards. And here's the big hop, followed by 3 little hops. Isn't he a good monkey? I decided to also look at this along with our monkey with a function machine, because you know I love function machines. So here's our function machine, and the function is y equals x squared. And this time, instead of just putting the rule on there, I made a very clear, boom, arrow, so you know which direction I'm going. And I'm going to take that 3 and run that 3 down the hopper and into the function machine. And you know that inside of there, he's going to be squared, and what comes out? Boom, 9. Now that's this function happening in the forward direction. Let's watch this same function, and you see it's the exact same function. I'm saying if you're going left to right, you're squaring. Oh, but now we want to go in reverse. So I'm going to put the 9 in the hopper. What's going to come out? Well, you know, we've also talked about interchanging inputs and outputs. That 3's coming out. Because if 9 was what it was when it was squared, 3 was what went in. Okay, well, since we just played with the x squared, here's my graph of y equals x squared, the nice purple parabola. Ooh, there we go. And you notice that I also put the y equal x line on here because now you know that there's a reflective property going on here. Well, let's complete this table of values because that will help me get this graph of the inverse. So if x is -2, plug it in, we come up with a 4. -1 squared is 1. 0 squared is 0. 1 squared is 1. 2 squared is 4. And if we take just a second and, wow, ugly 4, and take a look at that on the graph, we've got -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4. Now those are on the original function. By the way, this is the equation for f. Okay? Now to do the inverse, we go in reverse order. Instead of x comma y, we're going to go y comma x. Of course, we're still going to call it x then y. Here's what we're going to do. We're going to interchange these coordinates. So -2, 4 is on f. On f inverse, we've got 4, -2. Hey, by the way, I didn't really tell you about this notation. This little -1 sitting up here, as it looks like it's an exponent, that was the notation that was selected to indicate that this is inverse of f. Okay? So you may have a little x -1 on your calculator. Yeah, that doesn't have anything to do with what this is about. This is specifically saying we want to do the inverse function, and that says that you're going to interchange those x and y's. You're going to go in a backwards order of what the original function did. So we have 4 going to -2. We're going to have 1 going to -1. 0, 0. 1, 1. And 4, 2. Now remember, it's very easy from the graph of a function to graph the graph of the inverse. Now some people are really good, they have great visual skills, and you might be able to see what this looks like when you reflect it over that line. But there's lots of us that have trouble seeing that reflection over the diagonal line. And for that reason, I'm really focusing in that if you find some of these order pairs, it's a very easy process to switch the order and now graph your new order pairs. So I've got 4, -2. I've got 1, -1, which would be in about here. 0, 0, 1, 1, and 4, 2. And all the other points would also be switched around, and I get that cool little sideways parabola. Now, a couple of things. First off, taking into account I've got a little bit different scale horizontally and vertically, you can see that this is essentially a reflection down through there. It's also interesting that the points that hit right on the y equal x line, they stay put as you do that reflection. That makes sense. Now, somebody in the audience might be sitting there saying, oh, that's not a function. That's not a function. She is violating the vertical line test. Okay. As it turns out, if I do the inverse of this particular function, hey, he was a function. You can't growl at me about that. But his inverse ended up not being a function. Do you remember from way back when what we call that? That's a relation. Yeah, he is a relation, but he does fail the vertical line test. Well, you know, in math, a lot of times we do like working with strictly functions. So we need to be concerned about, okay, what will it take so that when I do an inverse, the result is also going to be another function? Well, what we need is, we need the original function to be what is called 1 to 1. Now you might say, what does 1 to 1 mean? Well, I've got a lovely illustration. That's 1 to 1. I think that one monkey would get really upset if the other one two-timed on her, right? Or on him, either way. When you fall in love, hopefully it's a 1-to-1 blissful relationship. Now, let's look at that in terms of the two functions we've talked about so far in this lesson. On this particular guy, if we identify a couple of points, like we have this 0, 6. Is that -6 shared by any other point? There's no other place that you get a -6. That means -6 is not two-timing that 0. They are paired together for life. They don't have to share each other's attention. Boom, 1 to 1. As you go up here, we've got the point 2, 0. Is that 0 being shared by any other point? No. Of course, sometimes to understand what something is, it helps to see when it isn't. So let's look at this guy. What if I take the point 2, 4? So 2 and 4 are happily paired together until 2 finds out that 4 has been double timing him, hanging out with -2. These guys are not 1 to 1 because that 4 is two-timing, okay? And you can figure that out really quickly from the graph by using the horizontal line test. Meaning this, if you can draw a horizontal line through your graph anywhere, and you catch that more than one time, you catch the graph, that means it fails the horizontal line test and it is not 1 to 1. Like here, I can draw a horizontal line test, it catches that graph twice, boom, he is not 1 to 1. Now what that means is he's fine as far as being a function, but his inverse will not be a function. And by the way, just so you might be putting everything together nicely, doesn't it make sense that if you're going to interchange x's and y's, then horizontal line test on the original becomes vertical line test on the inverse? That's the idea behind using the horizontal line test, okay? Now let's actually get into some of the meat of doing some problems related to inverses. So we still are working with our same old buddies, our linear function y equals 3x minus x, and our quadratic function f of x is equal to x squared. And I said I want to get the rule for the inverse, I want the domain for the inverse, and then prove that you have inverses. Okay, well, let's get started. So let's first look at our linear function y equals g of x, and that's 3x minus 6. And what I'd like to do is get the equation, which I often call the rule for the inverse. Now, chances are, if you've ever done this before, you probably remember, because it's one of those things that tends to stay in people's minds. You might say, switch the x's and y's, switch the x's and y's, I know what to do here. Yes, but you know what? Because it's so easy to get mixed up with which function am I talking about, let me give you a suggestion. I recommend that you start with your original function, write his name, and then write y equals the rule. See, what I want you to do is I want you to clearly lay out, here is my original function g. And I want you to have the x and y both in there. Because chances are you remember that to get the inverse, you're going to switch these two guys. So I'm going to have x equals 3y minus 6. Yay! Now, technically, that's a good relationship. However, we'd like to have that solved for y. So I can add my 6 across. X plus 6 is equal to 3y. Or 3y is equal to x plus 6. And then divide all the way through by the 3. Y equals 1/3 x plus, whoops, how about if I divide that guy too? 6 divided by 3 would be 2. Now, this has become g inverse, and so if you'd like to use the function notation, because you want to be cool, it would be g inverse of x is 1/3 x plus 2. Okay? Now, I don't know if my graph is still there if we'd go back, but you might take a minute and look back at the graph you made and see if we crossed the y-axis at 2. We had a slope of 1/3, up 1 over 3. I think that if you take a good look at that, you're going to find that is just the graph that we drew. Okay? So my rule for the inverse would be g inverse of x equals 1/3 x plus 2. Now for the domain. Sometimes people don't like to take my advice, and it's like, come on. I got these wrinkles from years of experience. Listen to me. To get the domain of an inverse, don't get the rule and then look at that. You might say, oh, but that's what I always do. Yeah, you'll be right about 90% of the time. The rest of the time, you'll be wrong. Okay? So if you want to be right all the time, listen. Remember that on the inverse functions, what we do is we switch the x's and y's. So what you do is you actually interchange. You actually interchange your domain and your range with g in order to get the domain and the range of g inverse. Meaning, if I want the domain of g inverse, I go looking at the range of g. And the range of g, he was that nice straight line, went all the way through the reals. So this guy's domain is the set of all reals. okay? But the reason the domain is the set of all reals is because the range of G was all reals. Please do heed my advice on that. Now, the last thing before we leave our friends here of G and G inverse is to actually prove that we have inverses. Now, the way that we go about doing that is we have to really verify that these guys will always undo each other. Because, you know, really, G inverse goes backwards of G, but then G should go backwards of G inverse. All right, it's a mutual kind of relationship here. So, to prove we must show that G composite G inverse of X. If I take X, I run them through the inverse, and then that answer goes through G, has to be the same as if I go the other way, and I have to get X. You say, what? Now listen really carefully. Remember that this composite means that you're going to run it through one, and then that answer goes into the other. What we're saying is start the whole deal with X. Okay, so I'm here. This is my beginning point, X. Then I operate through G. That takes me somewhere. Then I'm going to take that result and run it through the inverse. Shouldn't that take me right back to where I started? If these things are truly inverses of each other, they must undo each other. And by the way, function composition is not commutative, so I have to also try it the other way. Maybe I have to go left and then go right. But I have to show that going both ways, wherever I started, I end up at the same place. Okay, so it only takes us a minute to run these composite functions. Remember from having talked about the composites in a previous lesson that a good way to look at it is to change it into parenthetical kind of notation. Okay, if I run X into the inverse, what will I get? Well, this tells me right here. That's why it's one very good habit to get into, to always label your work. Okay, so I'm going to have 1/3 X plus 2. Yay! Now, this notation says take all of this garbage and run it into G. Well, G says whatever garbage you put in, we're going to take 3 times the input minus 6. And let's see what we get there. If we distribute this 3 through, won't we get X plus 6 minus 6, all looky there. Yay! That's what we wanted. And we algebraically showed that no matter what value you start with, you know what, I don't care if you call him Q or Z or star, but whatever you started out with, whatever G inverse did to it, G undid that, and you got back to your starting point. Now, remember, it's not commutative, so I have to go both ways. Now I say, okay, G inverse of G of X. I'm going to first take X and run him into the G function. Now, when I do that, let's see here, what do I get? G of X is 3x minus 6. Okay, 3x minus 6. Now, I'm supposed to take that garbage, all of that, and run it into the inverse. And the inverse says whatever your input is, multiply it by 1/3 and add 2. So 1/3 times 3x minus 6 plus 2. And if you distribute, you would get x minus 2 plus 2. Woohoo! I get x. And so you should take a moment and write a nice conclusionary statement. Therefore, G circled G inverse of x is the very same as G inverse circled G of x is equal to x, and thus I know their inverses. Okay? It takes just a few minutes to run through the process, and it's a good practice for you to do some work with your composite functions. Okay? Well, now let's switch to our buddy f of x. Okay? And you'll notice that I put a new little added statement in there right now. I said where x has to be greater than 0. Do you have any idea why I did that? Well, if we look back for just a moment at the graph of f, it happens to be right here, remember he's not 1 to 1? But if I only take the section where x is 0 or bigger, that's just this side, then he'd pass the horizontal line test and he'd be 1 to 1. So you see, this is really friendly now for me to work with it because he's actually going to be a function. Yay. Well, I've got a typo here, but that's okay. We can fix him. Rule for f inverse and domain. Okay. You know what? Let's find that domain first because remember I told you, don't you find the rule first. What I want to do is think. What is the range of f? And that means what kind of numbers are coming out of f? Well, I can get 0 and I can get positives, so I can get anything 0 and bigger. That would be the domain of the inverse. So in interval notation, it will be that. Okay? No matter what rule I get, that is the domain. And maybe it works great with the rule and maybe it doesn't, but that doesn't matter. That is the domain. Now, to get the rule, that takes just a little bit of algebra. So let's come over here. Let's see. F is the function where y is equal to x squared. Now, you realize I am rewriting that because we want to get the y worked in there. Because you know that to get the rule for an inverse, I switch x's and y's. So it helps to see where that y would be sitting. Now that means that for the inverse, I'd have x equals y squared, right? Well, now I need to solve it for y. And to solve it for y, I should square root it, because that undoes squaring. Okay, so y is going to equal, and you might say, oh, you got to remember to put that plus or minus on there. You know? Well, that's just not good. I don't want to get two different answers out. That wouldn't be a function. So then you think about it and you say, oh, well, you know what? If x was restricted on the original function to be 0 or bigger, what happens then to y on the inverse? Because remember, this is a total switcheroo. That means the y's have to be 0 and bigger. So I ignore the negative square root and I say there is what I want. So f inverse of x, remember that's what that -1 sitting up there in that superscript position means, is square root of x. So our rule over here would be f inverse of x is equal to the square root of x. Now I have to prove it. I have to prove that f and f inverse are really going to undo each other. Now, by the way, I'm assuming that you would probably accept that without me running through the algebraic process, but we will just to help you practice. Because don't you realize that squaring and square rooting are going to be inverse operations? See, I don't want you to lose common sense getting hung up with all the ickiness, okay? So here's what we would do. We must show that f circle f inverse of x has to equal f inverse circle f of x has to equal x. Now remember, the whole idea is that whatever I start with, I have to end with that if these guys truly are going to undo each other. All right? So I say, all right, let's start with this one. F of f inverse of x. Well, let's see here. If I put x into the inverse function, I get out the square root. Well, then what does the f function do? He squares it. So what do you get when you square square root of x? You get x. Now, by the way, technically, you need to make a little note to yourself. I'm very glad that x is greater than or equal to 0, because otherwise that may not be a true statement. Okay? Now, going the other direction, f inverse of f of x. When I put x into the original function, I get x squared. Then I'm going to take the square root of that. And again, you have to be a little bit careful working with your variables in this case, but the fact that I know x is 0 or positive, I can say that square root of x squared will be x, and I should include a conclusionary statement saying, hey, I know these guys are inverses because they will undo each other. Okay? Cool. Well, I think we've made a lot of headway. What I'd like to do is look at one more, and we're not going to go through the proof on this. Oh, I know. They get tiresome, don't they? Now, I've given you the graph of the function that we're calling f on this particular slide. And I'd like you to look at it really carefully. Now, we're going to be graphing these guys in a later lesson, but do you think that this guy is one-to-one? Do you think f is a one-to-one function? Remember, that means you can't be two-timing them anywhere. So you want to think, horizontal line test. Is there anywhere I could draw a horizontal line and catch this graph more than once? Now, I do understand that you might be a little bit concerned about what's happening here, but I can assure you won't be a problem. He will pass the horizontal line test. Now, why is that handy information? Well, that tells me that when I find this guy's inverse, he will be a function. Okay? Now, it also helps to see this graph to get the domain of the inverse, because remember, domain of f inverse is going to equal range of f. And you know, sometimes that range is a hard thing to find until you get really comfortable with these functions, but having the graph is really handy. So as you look at this graph, you can see that I'm hitting all values. I'm hitting all values. Now, you might be confused right around in here, but then I'm hitting all values again. As it turns out, we have what's called a horizontal asymptote running through there. I know, we'll talk about those guys later. we never hit 2. Now, I know that's not terribly fair to you right now, but I'm helping you out, okay? So I can say that this domain is all reals except 2. And here's one way you can write that, generally accepted by most math instructors. So that's the domain. Now, to get the rule, it's going to take me a little bit more algebra, okay? So let's come over here, get ourselves some workspace. Okay, remember, I told you, don't get yourself all confused of which direction you're working on. So start by saying f, my original function here. Y equals 2x minus 3 over x plus 1. Okay? Now, to get the inverse, what do? I interchange x's and y's. All right. So for the inverse, this becomes an x. Now, for the first time, we have more than one term with an x in it over here. Every one of those has to become a y. Oh, this could get ugly, huh? Because now we have to solve this guy for y. Well, the first thing we're going to do is multiply this y plus 1 over to the other side. So we would have x times y plus 1 is equal to 2y minus 3. Okay? Now, ultimately, I need to get the y's by themselves, so I'm going to distribute this x through over here. Xy plus x equals 2y minus 3. I want to bring this guy over, all right, because I want all the y's on the left. I'm going to take this guy over to the other side. So I have xy minus 2y equals negative 3 minus x. And the last, well, next to last move is let's factor this y out. I know you may not be comfy with every step here. That's why you got a pro to help you, right? Factor that y out because that gets him out there by himself, okay? And then this is multiplied on, so the way that you remove it is to divide it. Wow, that was kind of tough, but there's your inverse. Okay? So the rule for my inverse, if I want to go back into function notation, would be negative 3 minus x over x minus 2. Okay? I know, those are scary. Now, to kind of recap what's going on here with our inverse functions. And remember, inverse and reverse are not far apart in our language, and they're not far apart in concepts here. To graph the inverse of a function, interchange those x and y coordinates. So you might want to identify some points on the original graph, and then flip them to get your inverse. And remember, domain and range are switched. To get the equation of the inverse, okay, you're going to interchange the x's and y's. Now, remember that I strongly encourage you to pay attention to what's my original function, what's my inverse. Because otherwise, you get x's and y's just floating everywhere, and you forget which direction you happen to be going, okay? And then, lastly, now I have people try to bypass this and go different ways. No, stay with the theory. And the theory is that to verify that two functions are truly inverses of each other, that means not just that they sometimes undo each other or they kind of seem opposite. No. 100% of the time, they are going to undo each other. The way that you do that is to actually verify using composite functions and show that running those composite functions, no matter what you started with, those are your inputs in both cases, you always end up at where you started. Okay? Well, do plenty of practice, and I will see you in the next lesson.